Let's start today with my first speaker, Sascha. I want to welcome you on stage. He's the one I've been teaching courses together, so we've spent quite some time together in classrooms and traveling around the world. So Sascha, please do introduce yourself, and the auditory is yours.
Thank you. Hello, I'm Sascha. I would like to talk about how to create ROP-chains on ARC64. Yeah. As I said, I'm Sascha. I'm working as a security consultant for Recurity Labs. It's a small German consulting company. I do their reverse engineering. I'm interested in exploit development. I do mobile application security, embedded stuff. Yeah. What you will see here today, I will explain you the ARC64 fundamentals. I will give a short introduction in return-oriented programming, a short introduction into jump-oriented programming, and I will show you a very simple demo exploit. So why should you focus on ARM? Today, almost all smartphones and tablets based on ARM CPUs. Some computers today utilizes ARM CPUs. Many IoT devices, embedded systems, and also AWS offers EC2 instances which are based on ARM. So ARM is a RISC processor which has a small instruction set, a large register file, which means you have many registers. It's a load store architecture, which means that if you want to do something with data from the memory, you have to load it into registers or store it again into the memory, but you cannot modify the data on the memory directly. You have simple addressing modes and a fixed instruction size. And on the 32-bit architecture, you have conditional instructions. On ARMv7, which is 32-bit architecture, you have different states, the ARM state, thumb states, and many more states, some more states. You have 16 registers. Almost all are general purpose registers, but some of them are used for special cases. For example, the stack pointer, which is R13, the link register, which holds the return address, and R15, which is the program counter. You have several privilege levels, which are equal to the rings on Intel. So the user level, which is more or less ring 3 on Intel CPUs. Yeah, and the supervisor mode, where is the operating system, which is more or less ring 0 from the Intel CPUs. The ARM state is the default state. Here the instruction size, so all instructions are 32 bits, and all instructions have to be aligned, 4-byte aligned. All registers, so R0 till R15, are accessible here with all instructions. The ARM thumb state is introduced with ARM V4. Here the instruction size is much smaller. Here the instruction size is 16-bit, which brings you a better code density, and the alignment here is also 60 bits. But here only the R0 to R7 registers are accessible by the instructions, and the stack pointer, link register, and program counter. The ARMv8 architecture is the 64-bit architecture. It has also two states, the ARC64 state, which executes the 64-bit instructions, and the ARC32 bits for compatibility reasons. So, which means you can execute binaries for ARMv7 on that CPU as well. Here you have the A32 and the T32 bit state, which is more or less the ARM state from the ARMv7 and the thumb state from the ARMv7 architecture. On the ARMv8, you does not have privilege levels. Here you have 4 exception levels, which are more or less the rings from Intel CPUs. You have here 30 general purpose registers, which is X0 to X29. X30 is also a general purpose register, but is used as the linked register, which stores the return address. Then you have the stack pointer, the program counter, and a special register, which is X0, which always returns 0. On ARMv8, the stack pointer and the program counter are not general purpose registers, which means they can only be modified by special instructions. If you want to access the only 32-bit part, you have here the W0 and W29, which are the lower 32-bit part of the 64-bit registers. Yeah. As I mentioned, you have on ARMv8 exception levels. The exception level 0 is the normal user land exception level, where the normal applications are running. The EL1 is for operating system and kernel, EL2 for hypervisors, and EL3 is for secure monitor. Every function has a function prologue and function epilogue, which creates a stack frame, and at the end of the function, which destroys the stack frame again. On ARMv7, you will find such a function prologue, which pushes the link register, so the return address, and the frame pointer onto the stack, and then which creates the stack frame for the current function. On ARMv8, you have other instructions. So you have the store, the STP instruction, which stores 2 registers on the stack and moves the frame pointer to the stack pointer. The function epilogue, which is at the end of each function, removes the stack frame again and returns to the previous function. That can be done with a pop on ARMv7, which pops away from the stack to the program counter, or which branches to the link register, which holds the return address. On ARMv8, you cannot modify the program counter with a pop or a branch instruction. Here you have a return instruction, which means more or less pop to program counter. In the past, if you have vulnerabilities and you can execute code there, you could execute shellcode directly from the stack or from the heap. That means you have instructions in the shellcode which are placed on the stack, and then you jump to that code again. Yeah, shellcode is are the CPU instructions, which are mostly position independent, and yeah, the hex values of that instruction which are placed on the stack or on the heap. Here, for example, a simple buffer overflow. You have here a buffer which can hold 128 bytes, and then a string copy call which copies a message or something similar, which is given as an argument to the buffer without size checking here, which means that it could override or can override the buffer and the memory behind the buffer, which is a classic buffer overflow. In that buffer overflow, in the old way, you put, you write the shellcode into that buffer, you overflow the buffer ranges and overwrite the return address with an address of that buffer and jump back to the buffer and execute the shellcode. But nowadays, that won't work since the stack is not executable. So the AMD introduced the no execute byte, no execute, which is a possibility to mark the regions in the memory as not executable. Though that means you can write into the memory, you can read the memory, but you cannot execute instructions which are there. Yeah, and that is also introduced by ARM with the ARM v6 CPU. Yeah. Therefore, you have to use return-oriented programming. Here, it's a code reuse approach. That means you use existing code which is still in the memory. With return-oriented programming, you have to use so-called gadgets, which are small pieces of code. You can see two examples in the bottom of the slide, which ends with instructions that could modify the program counter. On ARM v7, that could be a branch to the linked register or a pop to the program counter. On ARM v8, you can only use gadgets which returns with return. So but the important thing for that gadgets is that they can restore or load value into the program counter. The shell code is then consists then not of instructions; it consists of addresses of gadgets. Yeah. And each gadget of that ROP chain calls the next gadget. Where can you find the gadgets? At least of the end of each function. On ARM v7 and Intel CPUs, there you have the advantage that you can find more gadgets, since you have different states on ARM v7. An application on ARM v7 could contain code for ARM and code for thumb state. And you could look for ROP gadgets which are for the thumb state in ARM code. And on x86, the instructions doesn't have to be aligned, so you can find gadgets everywhere you find the bytecode for the return instruction. So that can mean that if you have some data on the memory and there is for the opcode C3, which means return, you can find the gadget. On ARMv8, all instructions have to be 4-byte aligned, and all gadgets and all instructions are 32-bit. You can only find the gadgets at the end of each function. So that means you find less gadgets than on ARM v7 or on Intel CPUs. So that here could be an example for a gadget. Another important thing on ARMv8 is that you not only need a return instruction at the end, you also need a LDP instruction at the end, which restores the X30 register, which is the link register, which needs to hold the return address. So return jumps to the address which is stored in X30. So each gadget have to ends with that instruction, so which loads an address from the stack, puts it into X30, and then returns to that address. So that means in ROP-chain could look like that. So you have here some values which fills the buffer until the return address, and then you chain the gadgets, and you have all gadgets behind each other on the stack or in the memory. So here's a little example how the execution looks like then. So the gadget 1 is the return address which is currently in the X30 register. So if the return happens in the function call, it returns it, it executes the first instruction in our gadget, then it loads the next two values from the stack and puts them into X29 and X30, which is here that code and gadget 2. Then it returns to the value which is in the link register, which is the address to gadget 2. Then it executes here the first instruction in the gadget which we have here. Then it loads again the next two values from the stack, which is again that code and the address to gadget 3. Then it returns again to the link register value. And here in the last gadget, again, the first instruction is executed. Then again, the load and the return. Jump-oriented programming is very similar to return-oriented programming, but here the gadgets doesn't end with a return, it ends with a kind of jump, or a branch instruction here in that case. So that means here gadgets could be branch register or branch and link to register. BLR means that the address to the next instruction is written to the X30 register. So if we want to use jump-oriented programming, we need to prepare the registers, for example here X3 in the left gadget, with the next address. So how to find gadgets? It doesn't matter if return ROP gadgets or job gadgets. There are several tools online, for example ROPper or ROP gadget. So return-oriented programming on ARMv8 looks like that. If you want to prepare a ROP-chain, mostly you want to call a function or call a syscall. On both possibilities, you need to prepare the value, the registers x0, x1, x3, and so on, because those registers hold the arguments for sys calls or for function calls. So those registers have to be prepared. And therefore, mostly you need to read values from the stack. That means you prepare a ROP-chain. That ROP-chain or that gadgets read the values from the stack with a load P, for example, instruction into one of those registers. And then you fill all of the registers you need for your function call or for your sys call, and then you call the function or the sys call you want to. So here is an example for such a gadget which reads x0 and x1 from the stack and then reads x29, x30 from the stack and returns to that. The problem is you won't find gadgets which reads R0, x0, x1, x2 or those registers from the stack. You only find gadgets which loads the higher registers. So, for example, x20, x21, x22, and so on. The problem is now, how can you fill the lower registers with that? Therefore, you need to look for other gadgets like move x0, x20, which moves the content from x20 to x0. But you won't find ROP gadgets there. You need to use job gadgets there. So for a successful ROP chain on ARMv8, you need return-oriented programming and jump-oriented programming. Yeah. That means here, if you want to prepare for example, here the x0 register, you also need to prepare the x3 register, which calls the next instruction. So, vulnerabilities today are mostly on the heap, not on the stack. So you have double free vulnerabilities, use after free vulnerabilities, maybe buffer overflows, but on the heap. And then you have the problem that you cannot execute your ROP chain since the ROP chain relies on a stack pointer. Since the x30 register is always read from the stack and read to the R30 register. So what you can do here, you need to look for one gadget which moves your stack pointer to another region of the memory. So the region which is controlled by you then. Therefore, you can, this is called stack pivoting. You could use a gadget like that, which moves, for example, the x20 register to the stack pointer. For stack pivoting, you need to be very creative, since it's very hard to find gadgets which modifies the stack pointer directly, like as it's shown here. Another thing today is there are several other mitigations, exploit mitigations, like ASLR, stack canaries, control flow integrity. Mostly you need there more vulnerabilities. For example, if you want to bypass ASLR, you need a memory leak vulnerability, which gives you the possibility to read memory and get addresses from the memory, that you can calculate the read address. But this is not covered by that talk and demo, which we will show later. Yeah. Now we will look at a very simple example. We will look here at an Android application which utilizes JNI, which is the native interface, and here you also have C code then, which is executed. That Android application connects to REST service, gets JSON data from there, and pass that JSON data and call a native function. That is the JSON code, which is read by the application. There you have a length field and the message, which is base 64 encoded. The application will decode that message and give it to a native function, which does a mem copy at in the last line from the string to a buffer which has a size of 32 bytes without range checking and so on. So here you have again a simple buffer overflow which overrides the return address. So now the idea here is we will create a ROP-chain which executes a command with the system function which is in the libc. So for calling the system function, you need to prepare the X0 register with an address to the command. Since we will place the command also on the stack, we need a gadget which moves the stack pointer to the X0 register. Such a gadget could look like the gadget which is shown here. So we will look for a gadget which moves the stack pointer to X0, and most likely it branches to another register. So our ROP-chain will look like that. We will gadget which prepares the register for the branch instruction of the second gadget. And the second gadget is the move stack pointer to X0 register. And the second gadget then calls the system function. No. So we will use ROPR to look for gadgets. For simplicity, we will not bypass ASLR, so we will use fixed addresses. Therefore, I look for the base address of the libc. And set the image base here. We will use the LLDB server as a debugger on the Android device. And we will use the LLDB on this computer to connect to that process. And we will connect to the example, attached to the example application.
You're connecting to the real actual phone, right?
Yes. Oh. So, as I said, we will look for a gadget which moves the stack pointer to the X0 register. Therefore, we can use the search command in ROP-er. So we will see that we have here several gadgets. I will use that gadget since that moves stack pointer to X0 and do nothing else and branch to a higher register. Oh. So. So this application here is the REST service where the application connects to. And I prepared it for the ROP-chain. So I will put here the address of the ROP-chain, or of the ROP gadget. So now we can prepare X0 with the stack address. Now we have to prepare X24 with the system address. So to prepare X24, we need a gadget which reads the value from the stack and writes that to X24. So we have here one gadget which loads x24 from the stack, then x23, and here x29, x30, which we need for the return. So we will use this gadget. So this gadget reads from the stack pointer directly the 29 and 30 register, which is here. So we will need some value which is written into x29. Then we need here for the x30 register, the next gadget, which is this. Then it will load x24 and 23 from the stack pointer and offset hex 10, which is then here. So we need here the address to system. We need here any dummy value for x23. So and then here we will see at the end of that instruction the stack pointer is modified by 40 hex, which are some which we also need to put here. So we have here 8 hex 10, hex 18, hex 20. 28, 30, 38, hex 40. And then we will put here the command which we want to execute. So after that gadget, the stack pointer will point to that. And after that gadget, this gadget will be executed. That means the address of the stack pointer, which points to here, is then moved to x0. So now we need the address to system, which we can get from the debugger. I disassembled the system function, and then I have here the first instruction is the address of the system function. And I put it here. So that is now the complete ROP chain. It loads the values into 24 and 23. So this goes to x24, this goes to x23. Then it loads 29 and x30 from the stack. Modify the stack pointer to point to here. And then returns. With that returns, that gadget is executed. Since this is loaded to x30, this moves the stack pointer to x0 and branch then to x24. x24 is here filled with the system address, and that called system. For simplicity, I have prepared here some reverse listeners and so on that I can connect to localhost in order to connect to my device on port 999, which is the port that is used here by the netcat listener, which is started on port 999 on the device. So here you will see that Android is written here, which is here echoed to that listener. Yeah, that's it.
Awesome. So we are ready to question you, right?
Yes.
So my first question to you is, what is your favorite text editor? You were not prepared for this question, right?
No, I have not only one.
Only one?
I have not only one.
NeoVim.
I use several editors like Vim. I also use Emacs and Visual Studio Code. And
all right. I know that there are the automated tools to search and create the ROP chains and ROP gadgets and produce already the ready-made ROP chain for you. What is your take on this? Would they produce a good quality ROP chains or something that would never work and you always have to be there as an expert to review the automatically generated chains and modify them to the need?
There are several tools which utilize semantic search to create ROP chains, but I haven't used them extensively, so I don't know how the quality of that ROP chains is. The tools that I know, mostly you have to modify the ROP chains by yourself, but it's a good start.
Right. It is a good start because it will do a lot of work already for you, the heavy lifting. But you are the author for the ROPper, so when the ROPper will be able to support flawless ROP chain generation?
Anytime.
Anytime, so it's feature. All right, so for the Arch systems or Arch-based systems that we are currently looking at, I'm mostly in touch with embedded systems. Would you say that exploitation of embedded systems would pose any issues like having a limited libraries that will limit our chance to find the right gadgets to actually create a ROP or jump-oriented code?
Yes, less libraries means less gadgets.
Less libraries. So embedded systems that are like managing our daily lives, like transmission of the electrical grid, so they most likely are safe then from this kind of approach. What do you think?
I don't think so.
You don't think so? All right. So you said that you had some challenges with getting the stuff to work on the Android, and you said you needed time to fix this or figure out the way. So can you tell me what was the thing that you needed to overcome to make sure that your ROP chain worked? What was the thing?
On many embedded devices, you can use, for example, the system called mprotect to make the stack executable again. Then you can use any shellcode you want. But on Android, this does not work since they does not allow to make the stack executable, or they does not allow to make the stack memory executable if it's writable. So it's not possible to make the stack executable again.
And that's a protection feature introduced into the Android systems.
Yes.
So are there any other protection mechanisms, and how would you overcome them in principle, and we don't need a huge detailed. So is there, I don't know, a protection mechanism that would check if return has been called, also if the call exists, or that the stack pointer is always pointing in the stack, and if you're doing stack shift, it's not pointing somewhere else. So those checks, have you seen those on the Android devices or any other devices that would control and avoid mitigate these attempts to exploit?
I know Android uses several mitigations like control for integrity, which shall prevent ROP on Android devices. But not all, as far as I know, not all libraries are compiled with that protection mechanism. Yeah, ASLR is in place for all memory regions there.
So if you would have an ASLR here, because you explicitly said that you have disabled the ASLR. So if the ASLR would be, you have not disabled it.
I haven't disabled it, but the library, since on Android for the if you start an Android application, the Cygit process is forked, which means that the libraries does not place randomized again. So it just forks the process, and the libraries are on the same place as long as the Cygit process is not restarted.
So once they're loaded, they will be in the same position. That's what you uncovered and entered the right offsets and image bases. Yes. All right. Is there any other question from the audience? All right. I think the questions will come maybe afterwards. But Sascha, thank you for your talk here, and I do appreciate you coming on site. Additionally, I will give you a small token from the CERT.LV. This is something for you because I know you're now running off to the airport, and I really appreciate you coming over. Thank you. Thank you.
Thank you.